Hello, this is going to be test prep for test number 7 for 3004 in 2018, looking at test number 7 from 2017. Question 1. If we replace a fin with another material with a higher thermal conductivity, K, then figure out what happens to the efficiency and the effectiveness. All right, so the efficiency of a fin, given the symbol eta, is the heat transfer from the actual fin divided by the heat transfer that the fin would have if it was all at the same temperature. Constant temperature fin. Yeah. Okay. So that's the efficiency. So efficiency will go up if you do something to equalize the temperature of the fin, to make it all closer to the base temperature. And if you increase the conductivity of the fin, then that is going to be increasing the temperature, increasing how much the barrier is due to the convection at the surface of the fin rather than the conduction along the fin. So that is going to make the temperature of the fin more uniform, which should increase the efficiency because it makes the fin closer to the temperature at the base. So there's less of a difference between the heat transfer from the actual fin versus the heat transfer the fin would have if it was all at the same temperature, because the fin temperature is more uniform. Now compare that to the effectiveness. Effectiveness is the actual rate of heat transfer from the fin divided by the heat transfer of the base without the fin. So the heat transfer that you would have with maybe no fin. Okay, so the effectiveness is what would happen to that? Well, if the conductivity of the fin goes up, then you would have more heat transfer all along the fin. It wouldn't actually change the heat transfer that you would have from the base area with just the convection there, but it would increase the amount of heat transfer from the fin itself, so the effectiveness would also go up. And just as a check, you remember that these things are related. So the effectiveness of a fin is equal to the fin area divided by the base area times the efficiency. So we concluded that the efficiency would go up and that the effectiveness would go up, and according to this relationship between them, that also makes the we would say that efficiency goes up means effectiveness goes up as well. If we haven't done anything to this area ratio, then if one goes up, the other one has to go up the same way. Okay, next one's a little bit trickier. If we add a fan to blow air across a fin, then what should happen to the efficiency and the effectiveness? So your first instinct is, oh, efficiency is good, effectiveness is good, fan is good because it's going to increase how much the transfer happens from this fin, and so efficiency and effectiveness maybe will go up again. In fact, they actually both will go down. Now the reason for this is that if you add the fan, then the fin it's sort of the opposite of what we did in this last question, right? We've increased how much convection is going to be happening from the surface, or we've kind of reduced the convection resistance, which makes the conduction resistance a bigger deal. So the fin is going to be less of a uniform temperature, which means the efficiency is going to go down. Now, because the efficiency goes down, we haven't changed the area, the effectiveness has to go down. You can figure it out that way too. But why should the effectiveness go down by itself? Because the fin is kind of less efficient compared to the base. So it's not so much that the fin heat transfer doesn't go up. It does. It's just that increasing only the convection coefficient is going to increase the is going to have a bigger impact on the heat transfer from just the base compared to the heat transfer from the fin. So here we just have because the base isn't changing temperature, it's always just at the base temperature, we are going to have more of an increase in the denominator of this than we would have in the numerator increase, which means the effectiveness goes down as well. Okay, list 3 reasons why adding fins to the outside of a hot water pipe is better for heat transfer than adding them to the inside. There's a number of reasons for this. I can think of, I think, 4. So you want to add fins to the outside because they're going to fit on the outside. They might not fit on the inside of the water pipe, so you can add bigger fins if you add them to the outside. Number 2, there's more convection resistance on the outside, and so that's the place that needs the fins more, right? Like you want to the inside convection resistance is often a lot lower anyway, so that's not dominating this the total series resistance from convection inside, then conduction through the pipe wall, and then convection outside. The lower convection on the outside, meaning higher convection resistance, there is the one that's dominating. So that's the one we want to improve the most. Right. So a similar reason to that third one, to that second one there, is because the convection is lower on the outside, the fins are going to be more effective there. So if the convection is, if you have really strong convection, like you would in forced fluid flow, compared to maybe on the outside you would have free airflow. So free airflow on the outside is going to have a much lower convection coefficient, which means that the fins would be able to, with a reasonable conductivity, stay at a very high efficiency, and that's going to make them more effective compared to not having the fins. So per unit of material, the fins on the outside are going to make much more of a difference to that convection coefficient too. And that's a separate reason from the convection coefficient being a lot lower there. So convection resistance is higher on the outside, which means that's the one you want to improve. And the third reason is that the fins are going to be more efficient there than they are on the inside, so they make more of a difference. And the final reason is that adding the fins on the inside is going to have a detrimental effect on the fluid flow. So that means you're going to have to increase your pumping power. You're going to have more resistance on the inside. So that has some problematic impacts on the rest of the fluid system. So those reasons are: there's probably more space outside. The outside convection resistance is higher, so that's the one you want to improve. The fins do more of a, the fins are more effective at improving that outside convection resistance, and the pumping power that you have in your system isn't impacted by adding fins on the outside. Next one, do heat sinks often have a different thermal resistance when oriented horizontally rather than vertically? Explain. Okay, so if you go and look at the notes here, under the heat sink section, which is right at the end of chapter 17, section 6, then you see they often report a different resistance horizontally rather than vertically, and the vertical ones are smaller. So this is because once the fins, if the fins are oriented vertically, then the natural convection coefficients that are natural convection currents, the air currents that are showing up, are going to be flowing vertically past the fin, and there's less resistance to fluid motion in that direction. So it gets more air flowing vertically through it, which is going to enhance the convection coefficient seen by these heat sinks. So that's the reason. Okay, when insulating a pipe to prevent heat from escaping, other things equal, it's best to insulate with fins designed so that ML is equal to 1. Well, no. If we're trying to prevent heat from escaping, then having ML equals 1 is not a good idea. That's sort of a balance in what's going to be giving you a good amount of heat sinking happening from the fins for the cost involved. So going much past that is leading to diminishing returns in terms of the fin length that you're adding. But here, if we're trying to insulate, then you probably don't want to add fins at all, let alone add them to that length. At the critical radius of insulation for pipes. Well, again, no, the critical radius is the radius where the cylindrical insulating material is giving you a minimum for resistance. So that's definitely not the case either. You want a maximum for resistance if you're trying to prevent heat from escaping. With infinitely long fins, again, no, this is going to enhance the heat conduction, the heat transfer from the surface rather than decrease it. And definitely not all of the above. I don't know how you would do these simultaneously. That's ridiculous. So none of the above is the answer there. These are ways to increase the heat transfer from a pipe, not to increase the insulation. And last one, a reactor in the shape of a sphere holds superheated fluid at 500 degrees C in a steel, they give you the parameters of that, shell with an inner radius of 10 centimeters and outer radius is 12 centimeters. The outer surface has 50% of its area covered with fins that each have a base area of 4 square centimeters and themselves have an area of 20 centimeters squared with an efficiency of 80%. The finned and unfinned parts alike are subject to a combined convection radiation with heat transfer coefficient of 200 watts per meter squared Kelvin, while the inner surface is subject to convection with this coefficient. Then we have to find the thermal resistance of the shell. So that's the, not the convection resistance, but just the conduction resistance through it. Then the combined thermal resistance of the finned and unfinned outer surface. And if the reactor sits in a room with this air temperature, estimate the temperature of the unfinned parts of the reactor surface. So for the first part, we're just going to need the formula for a spherical shell resistor from the textbook. And if we go up to heat conduction in cylinders and spheres, we see that the conduction from a sphere with this little derivation there is working according to this resistance. So the spherical shell is going to have a resistance given by this. So this is outer radius minus inner radius over 4 pi times the conductivity and the product of the radii. Calculate the combined thermal resistance of the finned and unfinned outer surface. So this part is a little bit trickier. So we've got R. So first of all, just from regular conduction, we've got the R unfinned would be equal to 1 over H times A unfinned. Yeah, and then the resistance from the finned parts, well, we can figure that out by saying that the heat conduction from the fins is equal to the effectiveness times the heat conduction that you would have from the base of the fins by itself, which is actually the heat conduction, since the base area is the same as the unfinned area, because they said 50% of the outer surface was covered with fins. Then in this case, we could sort of rewrite that as the temperature difference. So maybe like the heat conduction of the unfinned parts, something like that. And why might that be useful? Because this would be related to the so now we can see how this is going to let us express the new resistance in terms of the old resistance. So the heat transfer is equal to the temperature difference divided by the total resistance. So that would be delta T over R, right? And that over here would tell you it's delta T over R unfinned, and we figured out R unfinned, so that's good. So this means that by rearranging things, we've got that the resistance of the fins should be equal to the resistance of the unfinned parts divided by the effectiveness. Okay, and then if we're going to be taking the finned and the unfinned parts in parallel, the total resistance of the surface would be equal to 1 over R finned, or maybe R fins, plus 1 over R unfinned, which is equal to 1 over the substituting in that the finned resistance is the unfinned resistance divided by epsilon. We're going to have this is just the unfinned resistance over epsilon plus 1. Okay, so we've got the unfinned resistance there divided by epsilon plus 1 as the total amount of surface resistance there. Okay, great. So now I think we can substitute in and calculate some things. I guess the last thing we'd want to do is remember the effectiveness related to efficiency from before. This is the area of the fin over the area of the base of the fin times the efficiency, and they gave you all of those things in the start. Okay, so then you could substitute into there and calculate those resistances. The final part says if the reactor sits in a room with an air temperature of that, estimate the temperature of the unfinned parts of the reactor surface. So for this one, we're going to have to use the total temperature difference to get the heat flow. So the total heat flow out is going to be equal to the total temperature difference divided by the total resistance which would be the T inside minus T infinity over R conv in plus R shell plus R surface, with the total surface resistance that we just used. Now, once we've got that, you can figure out what the temperature at some part of it would be. So let's say the temperature at the outer surface should be equal to the temperature far away plus the Q dot multiplied by the surface resistance. So this would be kind of going back in, saying the temperature drop across the surface would be the heat flow through it, rate of heat flow through it, that is, multiplied by its surface resistance. So then we'd kind of go back from the outer surface inside in order to figure out what that temperature at the outer surface is. Okay, so that's that. Now we can get to calculating. So let's see here. Got our computer algebra system of choice here ready to go. And T in is 500. We've got K is 50. R in is kind of R1 is 0.1. R2 is 0.12. We've got that the outer surface is 50% of the area. So maybe we'll say A unfinned is equal to A out times 0.5. We could figure out what A out is using the area formula for a sphere. So 4 over 3 times pi times R2 squared. And we have the effectiveness is equal to the fin area, which is 20 over the base area, which is 4, times the efficiency, which is 0.8. So that gives us an effectiveness of, should be 5 times 0.8, which is 4. Okay, so there we go. We can have a look so far. Yeah, effectiveness of 4. Then we've got our sphere is equal to R2 minus R1 over 4 pi K times R1 times R2. And there we go, 0.00833 divided by pi. All right. For this reason, sometimes I like to use just 3.14159 for pi and maple, just to force it to calculate using decimal numbers. So we'll see what we get for the sphere's resistance. Okay. Then the next part, we can calculate the unfinned resistance. We're going to need the H for that. H out is 200. H in is equal to 1,000. So that means our unfinned is equal to 1 divided by H out times A unfinned. And we next figured out that the surface resistance was the unfinned resistance divided by epsilon plus 1. So divided by 5 then. So the fins are helping a fair bit compared to just having that unfinned surface over the whole thing. So we would have only divided it by 2 if it wasn't for the fins. Next, the final part, we can figure out the total heat flow. Q dot is Tn minus T infinity. Did we call it T infinity? We didn't define that yet. Okay. T inf is 20 degrees, I think. Should be. Oh, it's down here. Yeah, 20 degrees. Okay, perfect. And then, so to get the heat flow, we take that temperature difference, and then we divide that by the total resistance, which was, we didn't calculate the internal convection resistance, but we can do that pretty quickly. 1 over H in times AN. I guess we need to figure that out too. 4 over 3 times pi times R1 squared. And then we'll add to that the shell, which I guess we've actually called our sphere. And then we'll add to that the surface resistance. And then to figure out the outer surface temperature, we will take T infinity and then add to that Q dot times our surface. This is going to raise the temperature. Right, so we've got an outer surface temperature of 287. If we wanted to know the inner surface temperature now, we could step a little bit further. We could say it's the outer surface temperature plus Q dot times our sphere. And then we could go further than that. We could say T in check maybe. So a check of the inner temperature would be T inner surface plus Q dot times R in, which we didn't define a variable for, but was equal to this. And that should get us back to 500. All right, so there we have it. Everything calculated up. We used we just substituted into all of these formulas with the parameters that they gave us and got our answers. Thanks for watching.